The purpose of this video is somewhat different than the other ones. The main purpose is to cover a couple of areas that were not previously covered adequately or not at all in the previous videos on matrix algebra. So let me just review again the adjugate of matrix A, or the adjugate is also sometimes referred to as the adjoint, although not in modern practice. The transpose of the cofactor C of A is defined as the adjugate of A equals C to the superscript T. Suppose A is n by n. The ijth minor of A, denoted m subscript ij, is the determinant of the n-1 by n-1 matrix that results from deleting row I and column j of A. The cofactor matrix of A is then the n matrix C, whose ij entry is the ij cofactor of A, which is the ij minor times the sign factor. So we then write it as follows, where C is given by this expression here. So what we do is, the key here is this part here. So we eliminate one of the columns, one of the rows denoted by I and J, and then we find the cofactor of that. The adjugate of A is the transpose of that C matrix, i.e. the n by n matrix whose ijth entry is the ji cofactor of A, and that's written as follows. And notice that we write the ji here, whereas up here we had ij, and the reason for that is because it is the transpose. The adjugate is defined as it is so that the product of A with its adjugate yields a diagonal matrix whose diagonal entries are the determinant of A, or the determinant dA. So then we get A times the adjugate of A is equal to the adjugate of A times A equals the determinant of A times this identity matrix, which is n by n. This implies that a fundamental result, this implies a fundamental result in matrix algebra, in which case the adjugate of A is equal to the determinant of A times A inverse. We can then solve that for A inverse, and we basically get Cramer's rule as we discussed in a previous video. A second thing that we want to look at is the Kronecker or tensor product. So we let A be a P by Q matrix and B an R by S matrix. Then A tensor product B is a PR by QS matrix. Note that this can also be written as A with a circle with a dot in it, B. And it too is, of course, a PR by QS matrix. So how do we define it? Well, A tensor product B is simply multiplying each particular element of A by the matrix B throughout. And that then results in a PR by QS matrix. Another topic we want to look at is Gauss-Jordan elimination. Consider solving this system of equations. 7x1 plus 3x3 is 4, 9x1 plus x2 plus 4x3 is 6, and 6x2 plus 5x3 is 6 as well. We set this up as an augmented matrix, where we have in the matrix, we have a matrix which we denote A, which consists of the various parameters of the matrix of the left-hand side parts of the equations that we wish to solve. So you'll see minus 7, 9, 0, 0, 1, 6. Those are the two columns in A, and 3, 4, 5 is the last column. Then we include an identity matrix, which is 3 by 3, because we have 3 equations and 3 unknowns. And then we have the vector of right-hand side values. And the purpose here is by using these elementary row operations. In this case, all we've done is we've divided the first row by 7. But in this second row, we've done a bit more than that, and I'll let you figure out what we've exactly done there. But we've added or subtracted a row from the second row in order to be able to get a 1 in this position. All right, that was the case. So basically, we had to get rid of that 9, and we did that first, and then we got rid of the 4. And we'll do that in this place here. We'll get rid of this. We need to get rid of that and rid of that one. And we do that, and we end up with this solution here. Now, the key that I want to point out is that once we've done this, we end up with an identity matrix over here on the left-hand side. This matrix, this complicated matrix, this one here, is the inverse of A. And this then is the solution vector. This is the solution vector for x1, x2, and x3. And if I do that, carry out these divisions, I get these numbers in this matrix here, which I have done using R. So you can check this using the inverse function in R. And we're teaching that in the labs. In the above, we used elementary row operations to move from one augmented matrix to the next. Did we use Gauss or Gaussian Jordan elimination? In Gauss elimination, we select a row to use to eliminate entries in rows below that row. In Gauss-Jordan elimination, we allow one to choose a row to eliminate entries in rows both above and below that row. So the key here is that Gauss elimination results in an upper triangular matrix, whereas Gauss-Jordan elimination results in an elementary matrix. And as you've seen from above, we end up with this elementary matrix, the identity matrix. So one last item that I want to cover here is floating point arithmetic, because I today encountered it as well. Computers usually represent 0 exactly as 0. Non-zero numbers are represented as the product of a t-digit signed fractional part and a scale factor 10 to the power e, where 0.1 is less than or equal to the absolute value of the fractional component denoted with an F here, and that's less than 1. And e is an element of the integers. On many microcomputers, particularly the older ones, t was set equal to 16, and in most cases it was 8 in the early computers, and e fell between minus 308 and 308 positive. Of course, these have been expanded on large computers, but even so, we run into trouble, as I'll note in a second. The first non-zero digit of F occurs immediately to the right of the decimal point. So we get, everything is in a decimal format. So you see a t-digit floating number. Thus, the 3-digit floating point representation of 0.05, if we want to represent 0.05, we end up representing it like this. The problem is that if we have 1/3 where it is 0.3333 ad infinitum, it must be truncated or rounded. It is not exact in a computer, and it can't be. So let's consider a simple example where t equals 2, and we want to evaluate 2/3 plus 2/3, so we want to add those together, which would give 4/3 minus 1/3, and that would equal 1. So 2/3 is evaluated in the computer as 0.666 and truncated because t is 2 at 0.67. So we add up 0.67 and 0.67, 2/3 and 2/3, we get 1.34. which because of t equals 2 is rounded off as 1.3. It'd probably be 0.13 10 to the minus 1. Then 1/3 is evaluated as 0.33. And finally, 2/3 plus 2/3 minus 1/3 is evaluated at 1.3 minus 0.33, which gives us 0.97, and the error associated with that is 0.03. Notice that 2/3 begin by taking 2/3 and subtracting 1/3, and then separating this part out, we get 0.67 related to this part, and we get 0.67 minus 0.33, which gives us 0.67 plus 0.34, which is approximately 1.0. So in this case, it is correct. Finally, at t equals 16, the result is 1.0. But with t equals 16, suppose we wanted to add 1/6, 1/6, 1/6, 1/6, 1/6, 1/6, 6 of those, which would give us 1, but it's not evaluated at 1, it's evaluated at 1 plus 10 to the minus 16. Now, you may not think that this is a problem with modern computers, but I recently had a case where I multiplied, where I had a matrix A, and I found its inverse, and then I wanted to check if it gave an identity matrix, and it did, sort of. What I ended up with was something like this. I ended up with 1.0, I had 1.0 times 10 to the 16th. I had a 0 and a 1 here, and here I had a number that was very, very small, to the 10 to the minus 16 as well. Not 18, it was minus 16. So that's how it showed up on the computer. Now clearly that's a 0, and this is clearly a 1, but it didn't come out that way. It made it look a little bit different. So you have to be careful when you work with these kind of numbers. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.